Cool. All right, so today we're going to be working through the slideshow again. We're going to be starting where we left off. We're going to be continuing working through Unit 3 of the Calculus textbook, which covers derivatives. So this is just a continuation of the slideshow from day 6, which we did not get to finish last time. Last time we went through these derivative rules. We explained all these derivative rules, why they work. Actually, sorry, these are the topics of discussion. I apologize. Last time we went through these derivative rules, explained why they work. This morning we did some examples. For the people watching this on YouTube, I didn't film the examples because they're just practice problems. But yesterday we just derived these rules, understood why they work, and made sense of them. So we did that yesterday. We're gonna skip the first topic of our topics of discussion because we did that yesterday. And we're gonna be discussing some terminology, more stuff on velocity as rate of change. I'm gonna keep beating the dead horse because I know I talk about that a lot, but we gotta keep talking about it. The idea of sensitivity to change, which is like a 1-second topic. It's really simple. Derivatives of trig functions will be the majority of the class. This thing called Leibniz notation and the idea of derivatives as peeling an onion, which I'll explain in a second, or when we get there. We good with that?
Yeah.
Cool. So the derivative at a point is often called the instantaneous rate of change of a function at that point. Because remember, when we first started talking about derivatives, we said a derivative is the rate of change of a function at a point, or the slope of a function at that point. And because it's the slope at a certain point or a given instant, we sometimes call the derivative the instantaneous rate of change of a function at that point. Does that make sense?
Yep.
Cool. All right, so I'm going to throw out a hypothetical. All right, and we're going to kind of work through this hypothetical and show how velocity is related to position. All right, let's say I'll go into Jamboard actually to illustrate this because this point is important. Let's say I wrote down some function, all right, that is a function of time. All right, and the function tells me how far I've traveled as a function of time. All right, so it tells me that the distance I've traveled is equal to the time that's passed squared plus the time that's passed. Do you guys kind of get what I'm saying here? We have my distance as a function of time.
Yeah.
Cool. So conceptually in the real world, if I asked you, what is the rate of change of my distance? If I asked how quickly is my distance changing, what real world phenomenon is that? And if that's a poorly framed question, I apologize.
It could be someone like walking, running, driving.
Exactly.
So another point.
Yep, exactly. So if I asked you if this function gave me my position, if I knew what my time was, if I asked you how quickly my position was changing, all right, or what the rate of change of my position is, could you see how that's just my speed, how fast I'm going?
Yeah.
How quickly my distance is changing is just how fast I'm going.
Yeah.
Cool. So what does the derivative, so if we took the derivative of this function, right, we would get the rate of change of this function because that's what the derivative does. It tells us the rate of change of this function. But the rate of change of position is speed. So if I took the derivative of this function, I'd get 2t plus 1, all right? So do you see how this new function would be our velocity as a function of time?
Yeah, okay.
Cool. So if the rate of change of distance is velocity, if we think about it in a conceptual real-world example, how fast my distance is changing is my speed, then if you have a function that tells you your position or your distance you've traveled, if you take the derivative of that function, the function you get is your velocity as a function of time. Does that make sense?
Yeah.
Cool. And here's a little a pop quiz, but not really. It's just a question. What do you think would happen if I took the derivative of this function? Well, first of all, it'd be 2, right? Would you agree the derivative would be 2?
Yeah.
What real life phenomenon is the rate of change of velocity? What describes how quickly my speed is changing? What physical property? Yep.
Acceleration or deceleration?
Yep, exactly. So in physics and math, we just call acceleration, I don't know if I spelled this right, I apologize, a change in speed or velocity. All right. So if you're slowing down, we would still just call that an acceleration because your speed is changing. If you're driving a car, you might say you're decelerating, right? But in math, we just say acceleration is a change in your speed or velocity. So it doesn't matter if you're speeding up or slowing down, it's still an acceleration because your speed is changing. All right. So do you see how if I took the derivative of this velocity function, right, the function I get, which is 2, would be my acceleration as a function of time? Because the rate of change of velocity is acceleration. Does that make sense?
Yeah.
Cool. And do you remember a couple days ago we talked about second and third derivatives, where if you took the derivative of a function and then took the derivative of that function, the new function you get would be the second derivative of the first function?
Yeah, I do.
Cool. So can you see now how acceleration is the second derivative of your position, the distance you've traveled?
Yeah.
So when you see in text people say acceleration is the second derivative of position, that's exactly this is what they mean. This is exactly what they mean.
Cool. Okay.
And I'll go a step further. If we differentiated the acceleration function, I wouldn't expect you to know what the next one is. So if our acceleration as a function of time is just 2, it's constant, our acceleration is always 2. If we took the derivative of this, we would get 0, right?
Yeah, because the rate of acceleration isn't changing.
Exactly. Perfect. You guys, that's amazing. You said it perfectly. Awesome. So the rate of change of acceleration, I'll tell you what it is and I'll explain why it is called, we call it jerk in physics. And the reason is it kind of makes sense in the real world. If I'm in a car with you, right, and we're standing still and I slam the accelerator, what's your head going to do?
It's going to jerk.
Exactly, right? And when I slam the accelerator, what am I doing? I'm changing my acceleration. I go from acceleration of 0 to a positive acceleration, right?
Yeah.
So jerk is caused by a change in acceleration.
Okay, yeah.
So we call the change in acceleration jerk. So you'd see that our jerk, if this is our distance traveled, if this is our position as a function of time, do you see how jerk would be the third derivative of position? Because we took the second derivative of position, acceleration, and differentiated that one more time. So then jerk is the third derivative of position. Does that make sense?
Yeah.
Cool. And in this example specifically, if this function was how far I've traveled as a function of time, right? We just showed mathematically that my jerk is 0. I have a 0 jerk.
Yeah.
So already, just from knowing this, we can, if this is a function that describes our distance as a function of time, just by using derivatives, we can extrapolate information out of this function, right? So we just showed, well, if this is my position as a function of time, that means my jerk is 0, my acceleration is 2, right? My acceleration is constant and it's 2. So just from taking the derivatives of this position function, we're able to extrapolate information about the way I'm traveling, which is useful.
Cool.
So a kind of problem I might ask you later is if I gave you this position function, I said, what's my acceleration? You would say, well, my acceleration is 2 and it's constant. So just from knowing the rules of derivatives, you can pretty much know in your head, just from looking at this equation, that if this is my position, then your acceleration is going to be a constant. Because when you do the power rule and then do the power rule again, because you're differentiating the derivative you get one more time, you're just going to get 2 as your answer. So just from looking at this, knowing derivative rules, you can say, oh, if this is my position as a function of time, my acceleration is 2, and it's always 2. So this idea is useful because, as you can see, we're transferring the idea of derivatives into the real world.
That makes sense.
Cool. So what we just did is we showed how velocity is the derivative of position, and we also illustrated what the higher order derivatives of position represent in a real world connotation. So remember how we did higher order derivatives and we kind of just explained what they were, but we didn't explain how they're useful?
type of derivatives?
Higher order derivatives. Like when you take the derivative of a function and then take the derivative of that one more time, we get the second derivative. We explained that last class or 2 classes ago, I forget. But we just explained that it exists. We didn't explain why it's useful. And you're probably thinking, okay, that's cool, but why does it matter? Why would you want to take the derivative of a derivative function? Here's why. Here's a real world application where differentiating twice is a useful thing because it gives us our acceleration.
Yeah.
Cool. So that's a use for higher order derivatives. And when we get to unit 4, we're going to be talking about more uses for higher order derivatives and why the second derivative is a useful tool. But that's for unit 4. We're on unit 3. So, all right. So that's that. The slideshow just, I think, goes over what I just said. It says the velocity is the rate of change of position. As a result, if I graph my position as a function of time, the derivative at a point would tell us how fast I'm going at that point in time. That's kind of what we just said. The derivative of position, the rate of change of position, is your speed or velocity, right?
Yeah, that makes sense.
So you could tell me how fast I'm going at t equals 2, but just calculating the derivative of that function at t equals 2. Cool. So in calculus, when we say rate of change, we mean instantaneous rates of change. We've been doing this secretly the whole time. When I asked you to find the rate of change of a function at that point, I really meant find the instantaneous rate of change at that point, right? So in calculus, when we say rate of change, we usually just mean instantaneous rate of change.
Yeah, that makes sense.
Cool. All right. So do you guys want to do a real life example of using derivatives again? Another real life example of using derivatives?
Sure.
All right. We're going to see how we can use derivatives to find the circumference of a circle if we know the area. And I'm going to walk you through it. I think it's cool. So let's say we knew that the area of a circle was pi r squared. And we do know that. Remember, we derived it at the very first lesson. I don't know if you guys remember.
Yeah, I do remember that.
But let's say we knew the area, but we did not know the circumference. We didn't know that the circumference was 2 pi r. We're going to pretend we did not know this. All right. We're going to see if we can figure out what the circumference is just by knowing this area formula. All right, and we're gonna do it using derivatives. All right. So here's my circle, right? And here's my radius. And I want you to watch what happens to the area as I increase my radius by some tiny increase in the radius dr, some tiny change in our radius dr. And I want you to ask, what happens to the area of our circle as we increase our radius a tiny bit? Well, the area of our circle also increases a tiny bit, right?
Yeah.
So if I increase the radius a tiny bit, our area increases a little bit. But remember how when we're dealing with tiny changes to a value in calculus, we mean a tiny change that's getting closer and closer and closer to 0, right? So if we imagine this change is getting closer and closer and closer to 0, then the resulting change in area will just be this kind of like infinitely small ring around the circle, right?
Yeah.
And I'll take a second to pause and make sure that makes sense.
No, that makes sense to me.
Cool. So if I asked you to find dr, the tiny change, dA, right? Actually, let me backtrack for 1 second. All right. So we know that the derivative of area with respect to radius, if we differentiate this function, because area is a function of the radius, dA over dr equals 2 pi r, right?
Wait, I'm a little confused.
Yeah, so I wish I had planned this out better because I know what this example is going for, but I forgot to run it through one more time to make sure it makes sense. Let me backtrack. I apologize for people watching. Let me backtrack and go back to the part that made sense. All right, so the part that made sense is if we increase our radius by some tiny value, right, we get this infinitely small ring around the circumference.
Yeah, I get that.
All right, so then a tiny change in area with respect to a tiny change in radius, if the tiny change in area, if our radius increases a tiny bit, all right, would you agree that this is just the circumference of the circle? This ring, if it gets infinitely small, is just the circumference of the circle.
Yeah, exactly. Yeah.
Cool. So what this means is a tiny change in area with respect to a tiny change in radius. Does that make sense? Like a tiny change in area caused by a tiny change in radius equals the circumference.
Okay, yeah.
Cool. So what is this? This is the derivative of area with respect to radius, right?
Yeah.
Cool. So why don't we just find the derivative of this? What's the derivative of this function? If our function is a and our input is r.
2 pi r.
Yep.
Is there an r?
Say that. Do you have a question? Say that.
Yeah, 2 pi r because 2 pi r.
Yep, the power rule. So then, if the derivative is 2 pi r, and we said, well, this derivative is our circumference, then the circumference is 2 pi r. And lo and behold, that's what we get normally, right? So isn't that a cool application of derivatives in real life? I think.
Yeah, that's pretty cool.
I think at least. So I apologize for the poor explanation at the beginning, but I hope the ending makes sense at least.
Yeah, that makes sense. That was perfect.
Cool. Awesome. All right, more velocity jargon. I'm just going to read this slide. I think we covered it all already. All right, this is just some stuff the textbook covers that I think it wants you to know, so I'll just say it. Using what we said, it's clear. Okay, this is just a repeat of what I said. It's clear how finding the derivative of a function tells. It's clear to see how finding the derivative of a function that tells us our distance as a function of time. If we find the derivative of that function, we get our velocity as a function of time. That's just what we talked about in the Jamboard a couple minutes ago. So speed is the absolute value of velocity, and I'll explain why I mean that in just a second. So velocity cares about your direction. Do you remember learning this in physics? Velocity cares about how fast you're going and also the direction you're traveling in. Do you remember that from physics?
Yeah.
Cool. Speed just cares about how fast you're going. It doesn't care about the direction you're traveling, right?
Yep.
Cool. So velocity does this weird thing in physics where if we're traveling forward, we would say our velocity is positive, but if we're traveling backwards, our velocity is negative. Do you guys remember? That from freshman physics?
Yeah, I think I do.
Cool. But can our speed ever be negative?
No.
Exactly, because our speed just cares about how fast we're going. So you'll notice that how fast we're going is the same as our velocity if we're traveling forward, right? Because when we're going forward, our velocity is positive, so it's going to be our speed. But when we're traveling backwards, our velocity is negative, so it can't be equal to our speed. But rather, our speed is the absolute value of velocity. Because if our velocity is negative 3 meters per second, that means we're traveling backwards at 3 meters per second. So our speed would be 3 meters per second.
Yeah, okay, that makes sense.
Which is the absolute value of velocity. All right. And the reason that's useful is because sometimes in calculus, what they'll do is, let's say you have your velocity as a function of time, or let's say you're writing velocity as a function of time. F of x is your velocity, and x is your time. All right. This is your velocity. We said that speed was the absolute value of velocity, right? So if I wanted to find my speed as a function of time, right, I would just take the absolute value of this function. Wouldn't you agree?
Yeah.
Cool. So you see how the blue one is our speed as a function of time, and the red one is our velocity as a function of time. And they're the same when they're both positive, which is what we said earlier. When velocity and speed are both positive, you'll get the same number. But when velocity is negative, your speed is the same distance from zero, but it's only positive because speed can't be negative.
Yeah, okay.
So if you ever got a function that tells you your velocity, if you want to find a function that tells you your speed, it's just the absolute value of that function.
That makes sense.
Cool. All right, I'll read this last point. Speed is the absolute value of velocity. We said this. We explained why it is, because velocity can be negative or positive depending on what direction you travel. But speed is just a number and hence is always positive. This goes back to vectors versus scalars. Remember, in physics, a vector is something with a direction and a magnitude. For example, force is a vector because you push with some amount of force. It has a magnitude, but you also push in a certain direction, so it has a direction as well. Temperature is just a scalar. It's just a number. We give a number to how hot it is, but we don't give a direction to how hot it is, right? It's like there's no direction to temperature, so it's a scalar.
Yeah.
Cool. And yet again, this means we can get a function for our speed by just taking the absolute value of our velocity function. And the last 2 points just explain what we explained a few minutes ago. Acceleration is the second derivative of position, and jerk is the third derivative of position. I'll give you guys a second to pause, write that down, and then we can move on to the very simple topic of sensitivity to change.
Almost up.
Ryan, how you feeling?
Feeling good.
Cool. All right, sensitivity to change. I don't know why I don't know why the textbook includes this because it's pretty self-explanatory, and you'll see in a second. A function is said to be sensitive to change if a slight change in its input causes a large change in its output. With this definition, I hope it's evident to see, and we'll do a diagram in a second to show how it's evident, that the derivative at a point is a direct measure of how sensitive a function is to change. All right, so if I drew some function, all right, we would say a function is sensitive to change if a tiny change in our input causes a large change in our output. So do you see how here the function is pretty sensitive to change because a tiny change in our input causes a large change in our output, right?
Yeah.
So do you notice how the derivative is an exact measure of sensitivity to change? The larger the derivative,
Yeah.
the larger the more sensitive the function is to change.
Yeah, that makes sense.
Cool. So here, would you say it's sensitive or not really sensitive to change?
Not super sensitive.
Exactly. So all I need you guys good with is the idea of sensitivity to change and how the derivative is a perfect measurement of that sensitivity.
I'm good with that, yeah.
Ryan, how about you?
Feeling good.
Good. All right, the derivatives of trig functions. All right, so I'm thinking what we'll get through the trig functions and then we might be out of time, but I at least want to get through the trig functions because it won't take too long, I promise. We're going to do the derivatives. We're going to learn the derivatives of trig functions, all right? And I could do it in 2 ways, and I want you guys to tell me which way you'd like me to prove it in. I could do it in a visual manner using the unit circle, or by using our limit definition, where we take the limit as h goes to 0. Like, for example, if we're trying to find the derivative of sine of x, we'd evaluate this limit. So I could either...
Do you have any preference? Nope, no preference. Okay, I'd maybe go with the first one, the visual unit circle.
Cool. I like that one better. All right. So let me draw my crappy unit circle. And if we cut out again, just come back and we'll finish up and you guys will be all good to go. All right.
Sounds good.
All right. So here's my unit circle. Here are my axes. We have my x-axis and my y-axis. And I'm going to draw a line up here with an angle theta. Right?
Yeah.
So then the height of the unit circle at this point would be sine of theta. Do you remember that from the unit circle?
Of course, yeah.
Okay. And the hypotenuse is obviously 1. All right. So remember, all derivatives is asking what happens to the output of our function if we increase our input by a little bit. Right? So I'm going to draw a change in our input largely, but in reality, remember, the change in our input would be close to 0. would be super small, right? So I'm going to change our input, which is the angle, by some d theta, some tiny change to our input theta. All right. And would you agree that the difference between the height here and the height here is the change d sine of theta, the tiny change to the sine of theta?
Yeah.
Cool. Cool. And let's go into Desmos really quick, and I'll graph the unit circle. All right. The unit circle looks like this. All right. I was confused for a second why that happened. All right. So here's our unit circle. Remember how we said when we zoom in really far to functions, they look like lines? Even though this is not a function, notice what happens as we zoom in far enough to the unit circle. What do we notice?
Yeah, it's turning into a line as well.
Exactly. All right. So I'm going to draw a diagram off to the side. Do you guys feel like you have this you have the setup in your mind?
Yeah, definitely.
Okay, cool. So I'm going to draw a diagram to the side, right? Where this is our tiny change in theta, all right? And if our tiny change in theta is really small, then it won't be an arc between these 2 points. It will be a line between these 2 points, right? Normally, when we have a circle and we draw an angle, right? If you the circle between these 2 points is an arc, right?
Yeah.
But if our angle is really small, which it is in d theta, remember how we showed that the line connecting them will be a line. The thing connecting them will be a line.
Okay. Yeah.
Cool. So, okay. So, here's our d theta. Here's our d sine of theta. All right. And here's our original angle theta. Cool with that?
Yeah.
And this is a bad drawing because it shows d theta as being really big, but in reality it's really small. So that's why there's a line between the 2 points, because when d theta is really small, the circle is a line.
Okay.
So
yeah.
Cool. Here's our original sine theta, right? And this is a 90-degree angle, right? Because our unit circle says that when we do these things, we get a 90-degree angle here. Right. So if all of the angles in a triangle have to add up to 180 degrees, this angle here is 90 minus theta, because theta plus 90 minus theta plus 90, we get a theta and a minus theta here, they go away, equals 180. So that's why this angle has to be 90 minus theta. Okay, yeah. Cool. All right. So when we increase our input by some d theta, we get another right triangle. Do you see that?
Yeah.
Cool. All right. So you'll notice that if we want to find out what this angle is, it's a very poor drawing. Do you notice how this angle plus this angle plus this angle have to add up to 180 degrees?
I do see that, yeah.
Okay, so then this angle has to be theta, because theta plus 90 minus theta plus 90 degrees equals 180. So this angle here has to be 90 degrees. Or sorry, not 90 degrees, theta.
Okay, yeah, that makes sense.
Cool. All right, let's go on to another slide. So what we've shown is the following, and I'll redraw it. My dog wants to get out. I'm just gonna let her out really quickly. All right. So we have shown the following. I don't know why my drawing skills are terrible, but alas. All right. So if this is our theta and this is our d theta, this is sine theta. And this angle here we said was theta using geometry rules, right?
Yeah.
If I connected a line from here to here that formed a 90-degree angle, right, we get this. Let's look at this triangle. And remember we said that the difference in height from here to here is d sine theta? So this side of the triangle is d sine theta.
Okay, yeah.
Cool. And do you remember that in our unit circle that whatever our angle is the length of the arc? Because the circumference of the unit circle is 2 pi, right? Because 2 pi times 1 is 2 pi.
Yep.
And 2 pi radians around the circle, right, would give us actually, let me backtrack. If we only traveled pi radians around the circle, if we made an angle that was pi radians, so this, you see this angle here is pi radians.
Yep.
How much of the unit circle have we traversed? Well, we traversed pi of the circumference. We've done half of it, right? So do you see how the angle that the two lines make is the length of the arc between them?
Wait, say that again?
So do you see, I'll do another example. When our angle is pi over 2, right? 90 degrees is pi over 2.
Yep.
How much of the units, how long is this section of the unit circle? It's pi over 2 as well, right?
Yeah.
So do you see how the angle that two lines make tells you the length of the arc between them? They're the same.
Yeah.
They're the same. So if our angle here is d theta, then this, even though it's a line, it's still an arc between the 2 points. It's still, right, it's still on the circle.
Yep.
That would be d theta.
Yeah.
And would you look at this? We're going to do something cool. If I take d sine theta and divide it by d theta, would you agree that that's the derivative of sine of theta?
I would agree, yeah.
All right. Here is our angle theta. And d sine of theta is adjacent, and d theta is hypotenuse. We're doing adjacent over a hypotenuse. So what is that?
The cosine?
Exactly. So the derivative of sine of theta is cosine of theta.
Dang, okay. That was pretty sick.
Cool. And if you go here, bada bing, bada boom, that's what it says.
Damn, nice.
Awesome. Does that make sense?
Yes, sir.
Awesome. All right. So we could go through. So
we should write down all of these.
Me?
Yeah. Should we write down all of these?
Yeah. I would write down these definitions. Yes.
Okay. Cool.
So I'll pause to do that. And while you're doing that, I'll ask a question. For the proof of why the derivative of cosine is negative sine of x, we do the same process, but with the cosine. So we use the we don't use the height, we use the length. So if you guys don't want me to derive that, that's fine, because you guys still understand the process for finding the derivative of cosine. We would do the same kind of process with the unit circle. So if you guys are fine with not going through the derivation of the derivative of cosine, I'm fine with that, because I know that you guys know the process because it's the same as sine.
Yeah, that's fine with me.
Okay. And for the other ones, I'll show you how just by knowing the derivatives of sine and cosine, we can find all the other derivatives. But write these down, and then we'll get to that in just a second. I think the meeting is going to time out in just a second. So why don't you guys write these down, and when the meeting ends, or when you guys are all done, we'll either end the meeting or the meeting will have ended, and we'll just come back and finish up our last thoughts.
Sounds good.
Again, my inner math freak and my inner math geek. Isn't it really cool that the derivative of sine of x, the derivative of one of the major trigonometric functions, is the other major trigonometric function? It's a really cool coincidence, I think.
Yeah, I do think that's really cool.
So I don't know. To me, that shows how math is really beautiful, and it really plays out. All right. Ryan, how about you?
Yeah, I got them.
All right. I'm going to end the meeting and I'll start it in just a minute. Okay. Or I'll start it right now. All right. All right.
Yeah.
See you guys in a second.